We're going to shift gears now and talk about error in chemical analysis. And so the first thing I want to do is talk about error in the context of science, what we mean by error, what the magnitude of errors that you see occur in chemical analysis are, how you should deal with error, and the impact of gross errors, or what Harris calls in their textbook blunders, on chemical analysis mean for the greater scientific community. So error is discussed in chapter 3 of Harris, which is part of your assigned reading for the week. And we're going to go through error over the course of the next couple of days and then segue from error to statistics, the mathematical means by which we judge error. The first thing I want to do is put scientific error in a little bit of context, because a good concrete understanding of how we measure and how we look for error in experimental design and experimental execution is one of the most fundamental but most often overlooked skills in being a good scientist and certainly in being a good analyst. So first thing, just a general statement. In any experiment, you have some error, because any experimental measurement you perform is subject to both systematic and random errors, as we're going to see shortly. This means that we don't just get to throw the whole experiment out the window and say, why measure anything? Instead, a fundamental part of being a good analyst is improving your technique and understanding the components of your experimental design so that you can get your experimental work down to the point where the values that you measure are only being influenced by the smallest systematic errors, which have been corrected for, and inescapable small random errors that are fundamental to the tools we use to measure specific quantities. So your goal as a good analyst needs to be to minimize experimental error. We can never escape it completely, but a good analyst that pays careful attention to their technique and understands how the design of their experiment works to give them their result can actually whittle down the error associated with their experiment to a very, very small margin and achieve very good results consistently and reproducibly. But we have to recognize and be a little bit humbled by the fact that no matter how good our analytical methods look on paper, there's always the potential for error. And in this module, we want to address, where does error come from? How can we account for it? And how can we use what we call propagation of error to judge whether an experimental design is suitable? The most catastrophic of errors in science, what we call high-profile errors, or these gross errors or blunders, can have significant ramifications for you as a professional scientist, for the scientific community, and for the whole course of a discipline. And so one thing that I'm going to call on you all to do, starting with your lab work this term, if you haven't already started, is to really get into the habit of honing your scientific skills and developing the tools you need to avoid gross errors. And if you experience a gross error, know how to deal with the data that comes out with that trial and be willing to step away and say, the results I got in this trial were influenced by a gross error. I'm going to improve my technique. I'm going to make sure it rarely happens again and I can't use the information from this trial. Because a gross error is a severe error in technique, technical execution, or experimental design in which you end up doing something either accidentally, in the sense that you didn't mean to design the experiment that way, or accidentally in the sense of you made a mistake with your technique in the lab that leads to part of a sample being lost, an experiment being run at the wrong pH, or some other significant error which would affect the concentration of the analyte that you're reporting. So as quickly as possible with young scientists, we want to instill good habits, get you to the point where you're very rarely making gross errors. And when you do make them, you know how to deal with them. Because even amongst professional scientists today, gross errors happen far too often. And when they do happen, you need to understand there's very real consequences for reporting experimental results that have a gross error in them and your name is attached to it, or your lab's name is attached to it. Gross errors that are included in final chemical results, but not reported or not identified, are the types of errors that can cost scientists their job, put the reputation of the lab or the corporation that they're working for in jeopardy, and may constitute an ethics violation. So you have to recognize that when we talk about gross errors, these are something we want scientists to avoid at all costs, but they're still far too common in science. And when they are revealed and when they're finally realized, they're the types of things that can really call the reputation of practicing scientists and their ethics into question. So there are a number of these kind of high profile examples of gross errors in professional science that we could point to. One of the most significant to come to light recently involved a public health lab in DC, which got a new director, Dr. Anthony Tran, in late 2016. And when Dr. Tran came in, he noticed something very disturbing in this DC public health lab's handling of Zika virus samples. So as a reminder, Zika is a mosquito-carried virus that can impact human beings. It can be passed into humans through mosquito bites. It's more common in tropical environments and environments near the equator, but Zika-carrying mosquitoes have now spread well to the north of the equator and well to the south, and this virus-borne disease is pretty much embedded in most Western Hemisphere mosquito populations. And prevention of this virus is one reason why most communities in the United States have become so aggressive about spraying mosquitoes. The virus doesn't usually cause adult humans that many significant health concerns. You may have a period where you have severe headaches, fatigue, cough, but in general, the virus is not usually lethal to most adult humans and doesn't cause significant lasting health problems in most cases. However, if the virus is spread to a developing human fetus, the consequences of the virus for young humans and a human fetus inside its mother's womb are significant and lasting. And one of the most dramatic of these are the development of what's known as microcephaly, or an underdeveloped cranium and forehead, where babies can be born with significant birth defects to their head and their other limbs. So Zika has become a severe health concern in the past 3 years, and this lab in Washington, D.C. was charged with monitoring Zika cases coming into the United States through DC's international airports, DC's port, and other routes of entry into the country. And when Dr. Tran took over this DC public health lab in late 2016, he noticed something very disturbing, which was the results for Zika were uniformly negative coming out of this health lab. No matter who they tested, they never found any positive Zika cases in any human subjects that reported or gave blood samples to their lab. And this is something that should have rung an alarm bell right away, because in New York and Los Angeles and Chicago and every other major US city, you had a significant number of Zika positive travelers either coming home to the United States or coming into the United States on visas, etc., from other countries. It turns out that when Dr. Tran got there and began to head up this lab, he noticed that they were running their Zika assay incorrectly. They were diluting all their samples for testing far, far too much, and they were diluting the Zika markers and the proteins associated with the virus's coat past the point where standard assays could actually pick them up again. So this was a huge public health concern, and one that the lab was ultimately liable for, both in an ethical sense and a legal sense, because you had many people who had sent samples of their blood to the lab for testing to determine whether they had Zika or not. And for at least a year, the lab had been reporting, no, you don't have Zika, you're fine, when in fact, many of the subjects were Zika positive and the lab hadn't spotted it. So in the course of our lecture today, we're going to introduce you to the possible sources of error in the lab, and we're going to talk about how chemists and scientists divide up the various types of error, looking at systematic, or what we call determinate error, random or indeterminate error, and last but not least, at gross error. And so our ultimate goal for this module will be to train you how to recognize how much error is associated with a particular experimental method through what we call propagation of error, but also we just want you to be aware of the error associated with any experimental measurement and the implications of that error for the study that you're trying to do. Rule number one, mind your own technique, develop your own technique, and get sensitivity early on for whether you are actually committing some type of significant or gross error in procedure in the lab. And if you have a question about a technique or how to run an analysis, always ask, always double check, always design your experiments so that you're using controls and quality controls to make sure that your assay is appropriate for the experiment that you're trying to run. Gross error is avoidable, and the sooner that young scientists develop good experimental habits, the easier it's going to be to make that transition into a professional science capacity where you know that everyone can trust the data that you're generating and you're designing the best experiments you possibly can.